However, at A level, I don't think you look at those reactions at all. What you do look at is the so-called Azo coupling. So here's our aryl diazonium cation here. React that up with drawing phenol here, then you can get reactions at the 4 position across from the phenol, or if there's something there, it would actually work at the 2 position. This is a very, very, very weak electrophile. It's got that positive there, so you'd think, oh, it's an electrophile, but it's a relatively weak electrophile. It needs a very reactive aromatic to react with. But when it's got a reactive aromatic, like phenol here, you can get electrophilic substitution. So pi electrons here from this double bond come down to the nitrogen, pi electrons move from the nitrogen to the nitrogen that's formerly positive, and you get a substitution right here. Now, of course, ordinarily we draw the pi electrons coming in here, so there'd be a positive charge on this carbon, but I've gone straight ahead to going to the resonance structure that has the positive charge on the 4 carbon, the positive charge where this phenol was. Okay, so I've moved those pi electrons here as well, because in a minute we'll come back and point out how important that is. Anyway, here is of course that intermediate that we could have drawn as the Wieland intermediate. We then deprotonate, take the electrons from the carbon-hydrogen bond, put it back into the benzene ring, and we make this lovely product here that is called an azo compound. Now, I mentioned that it was really important that you had to look at this resonance structure because this oxygen, of course, has a lone pair, and so it can delocalize that positive charge even more. And I'm not going to dwell on it. You can go and look at the aromatic extension topic for it. But having that oxygen there at that 4 position, or if we were to do it, if that 4 position was blocked, having it at the 2 position here, means that we got extra reactivity, extra stability of this intermediate. This azo coupling doesn't work if you just got a benzene ring. You have to have the phenol, or you have to have some kind of amine here at that 4 position across from where you're going to do it. But anyway, you can make a whole series of these azo compounds with different substituents on the benzene ring that was originally part of the diazonium cation. Probably not too many substituents on this original ring, but you have the phenol possibility and also having amine possibilities up here. What's cool about these azo compounds is they are often deeply colored, and they're extensively used as dyes. They're extensively used as food colorings. In fact, these 7 food colorings that are still legal, 3 of them are azo compounds. There was a 4th and a 5th, but they were found to be nasty. Anyway, the reason why they're colored, and I'm not going to dwell on this here because we talked extensively about the reason for color back in the transition metal compound module. Transition metals are colored because electrons can move from one d orbital to another d orbital, absorbing the appropriate amount of energy. And the energy difference between those d orbitals corresponded to the energy of visible light. We have exactly that same thing for these azo compounds. You have a very extended delocalized pi system. You've got the pi clouds here, the pi clouds here, the pi clouds here. You can extend those electrons all the way through this long molecule. So a very extended delocalized pi system. And when you have extended delocalized pi systems, well, then the highest energy bonding orbital, so the highest energy that's got electrons in it, and the lowest energy either non-bonding or anti-bonding orbital is very close in energy together. In fact, these energy levels are so close together that the energy between them corresponds to visible light. So you shine visible light onto an azo compound, photons of just the right energy will be absorbed by one of these electrons. It will pop up there. It will absorb those photons, and so you will see a color. Further discussion of that back in the transition metal complex, but what's important for A-level is that these azo couplings, so that's with a diazonium cation, an aryl diazonium cation, with a very reactive aromatic compound, either a phenol or another aniline or some version of an aniline, gives you these azo coupled reactions, very nice and coloured because the pi electrons spread out all over there, all through the molecule, therefore giving you very close bonding, non-bonding or anti-bonding orbitals so that electrons can pop from one to the other, absorbing visible light photons. So that's the end of the amines. Hope you enjoyed it.